So imagine you have this really brilliant colleague, right?
Okay, I'm picturing it.
You hand them a massively complex Python code base. Like it's just riddled with subtle logic errors.
A total mess of a script.
Exactly. And they debug it in seconds. Just boom, done. Then you ask them to break down the mathematical probability distribution of, say, a catastrophic moral dilemma.
Right, something super heavy.
Yeah. And they map out all the competing philosophical frameworks flawlessly. Just incredible graduate level reasoning.
Okay, sounds like a great colleague to have around.
Right. But then you hand them a match, a candle, and a box of thumbtacks. And you ask them to attach the candle to the wall.
Oh, the classic Dunker candle problem.
Yes. And their brain just like literally shuts off.
Utterly paralyzed.
Completely. They just stare at you. They're utterly unable to comprehend that the box holding the tacks could, be emptied out and used as a shelf.
Yeah, it really is the ultimate paradox of modern machine intelligence, isn't it?
It is. It's so weird.
We've built these localized architectures that can navigate these incredibly dense, high-dimensional vector spaces. They simulate graduate-level reasoning,
Right.
yet they completely lack the basic, grounded physical intuition of, like, a toddler playing with wooden blocks.
It's wild. And that's exactly what we're diving into today. We are dissecting those fascinating, brilliant, and honestly sometimes fundamentally broken AI brains.
You've got a lot of ground to cover.
We really do. So we've been handed this massive, meticulous set of testing logs from an independent investigator.
And this investigator spent weeks, right?
Weeks just putting the current crop of local AI models through an absolute gauntlet.
Which is so valuable for us to look at.
Totally. We're digging into the raw chat logs, the failure states, the underlying transformer mechanics, because we want to definitively answer one question for you.
What is the absolute best local AI to run as your daily driver right now?
Exactly. Now, context is critical here. The investigator's logs are dated Sunday, July 12th, 2026.
Right. Which means things are moving incredibly fast. If you're running local models on consumer hardware, you know this landscape shifts monthly.
Oh, totally. Like whether you are leveraging the unified memory of an M-series Apple Silicon chip, or maybe you're wrestling with the VRAM bottlenecks of dual consumer GPUs over a PCIe bus.
The struggle is real there.
It really is. What reigns supreme today might just be totally dethroned in a few months.
Which is why understanding the investigator's methodology is actually just as important as the results themselves.
Yeah, definitely.
If you understand the underlying architectural bottlenecks and why these models fail so spectacularly in specific edge cases,
You essentially equip yourself to evaluate whatever foundational model drops next quarter.
exactly, you have the tools to test it yourself.
Right. Before we jump into the methodology, though, we should probably quickly define what we mean by local AI for anyone who might just be getting into this deep dive.
Sure, so unlike massive cloud-based models, the trillion-parameter behemoth running in giant server farms, local AI refers to smaller, highly optimized models.
Models you run entirely on your own personal hardware.
Right, your laptop, your desktop. This ensures absolute privacy, it gives you offline capability, but, and this is the big catch, it requires intense optimization to run smoothly.
You can't just throw raw compute at it. You have to be smart.
Precisely. You are constrained by your own RAM and GPU memory.
Okay, so let's start with the investigator's evaluation matrix. Because evaluating an LLM for daily local use, it is not the same as benchmarking one of those massive cloud models.
No, not at all. You need a completely different approach.
The investigator used this really strict 85-15 weighted formula.
I love this formula. It's very pragmatic.
Right, so 85% of the final score is determined by reasoning and answer quality. But that remaining 15% is dictated entirely by practicality.
Specifically, token generation rate.
Speed.
Yeah, speed. The 85-15 split acknowledges the harsh reality of consumer hardware. Because, if we ignore token generation rate, we just end up praising models that are functionally useless for a daily workflow.
Right. Nobody wants to wait 5 minutes for an email draft.
I've seen developers try to daily drive a 70 billion parameter model that's been quantized down to its absolute limit on insufficient VRAM.
Oh, man. That sounds painful.
It is. The reasoning might be solid, but they are looking at, 2 or 3 tokens per second.
Just agonizingly slow. For context, tokens per second, or TOSes, is literally just the speed at which the AI types out text, right?
Basically, yes.
I always look at it with this analogy. If it's writing a brilliant essay at 3 tokens a second, it's like watching a master calligrapher.
Oh, that's a good way to put it.
Right. Like, the output is beautiful, but it is just agonizingly slow for a quick chat. You need it for a quick refactor of some code, and you're just sitting there watching it draw each letter.
Yeah, for a daily driver, you absolutely need a balance of brain power and typing speed.
I kind of look at token generation rate versus time to first token, or TTFT, as a cognitive flow issue.
How so?
Well, if I am using a localized model to refactor a block of code, a slow TTFT breaks my concentration. I'm waiting for it to start.
Right, you get distracted.
But a slow token generation rate is even worse, because it forces me to watch the model think at a fraction of my reading speed.
Yeah, you're just staring at the cursor.
Exactly. And the investigator's log suggests that anything below 15 tokens per second completely disrupts human-computer synergy.
You really need the model's output velocity to roughly match your own skimming speed.
Which means you are constantly balancing model parameters against your hardware's memory bandwidth. It's a tightrope walk.
It is. So, to test this balance, the investigator designed this brilliant 10-question gauntlet.
It wasn't just random questions, right?
No, not at all. It was specifically engineered to stress test how well these highly compressed models maintain their latent space integrity under varying types of cognitive load.
Like a diagnostic tool for the AI's brain.
Exactly, probing different regions of the model's architecture.
Looking at the logs, it's a really great cross-section. It starts with simple, deterministic fact retrieval.
Like asking for the primary function of mitochondria.
Right, the powerhouse of the cell, which just tests the baseline integrity of the model's training weights. Does it know basic facts?
But then it immediately escalates. The investigator throws them into counterfactual reasoning.
Oh, yeah. The question about what happens to global trade if the Suez and Panama canals close permanently overnight.
That specific question is tough because it forces the model to traverse its semantic network.
It has to connect things that aren't usually connected.
Right. It has to dynamically link isolated concepts like maritime shipping routes, supply chain elasticity, geopolitical stability, all without relying on a pre-computed string of text from its training data.
It actually has to reason through the scenario.
Exactly.
And from there, the gauntlet just gets harder. Strict logic constraints, lateral thinking, ethical synthesis, and Python debugging.
It's designed to find the exact point where a localized model's attention mechanism just collapses.
And oh boy, did they collapse. Let's look at the ultimate stress test for state tracking from the logs. The river crossing puzzle.
This is a classic. The constraint satisfaction problem.
Right, so the setup is a man has a fox, a chicken, and a bag of grain.
We all know this one from childhood.
Yep. He has to cross a river in a boat that only holds him and one other item, and the constraints are rigid.
The fox cannot be left alone with the chicken.
Right, fox eats chicken.
And the chicken cannot be left alone with the grain.
Chicken eats grain. So why is this such a brutal test for an AI?
Because when you feed this to an LLM, you are essentially launching a targeted attack on its key value cache, or KV cache.
Okay, break that down for us. What does that mean in this context?
Well, to solve this step by step, the model has to maintain a continuous, flawless vector representation of the physical location of the fox, the chicken, and the grain.
It has to hold a mental map in its head.
Exactly, across a shifting temporal axis, step 1, step 2, step 3. If those embeddings bleed into each other, if the model forgets where the fox is on step 4, it loses track of reality.
So it's a test of object permanence, basically.
In a mathematical sense, yes. I would argue it's less about the raw capacity of the KV cache and more about how the attention heads prioritize those cache tokens.
Because a localized model has fewer attention heads than a cloud model.
Right. So as the context window grows with each generated step of the solution, the semantic weight of the initial rules, the constraints, starts to dilute.
The rules just sort of fade from its memory.
Exactly.
And that dilution is incredibly obvious in the investigator's logs for the LFM 2.5 1.2b models.
Oh, the 1.2 billion parameter model.
Yeah, which is microscopic in AI terms. I mean, it's built for blazing fast generation. It was hitting 40+ tokens per second.
Just screaming fast.
But its state tracking was non-existent. Like, let me read you the output from the log because it is hilarious.
These do.
Okay, so it starts fine. Step 1, it moves the chicken. Good job. Step 2, man returns alone. Perfect. Then step 3, it outputs this exact string. Take the fox across. Fish, in parentheses, fox is now on the other side. Result. Man has one item, fish, fox, and grain.
Wait, it mutated the fox into a fish.
A fish. It just casually invents aquatic life mid-sentence.
That's amazing.
And then the best part is the model's own output triggers a localized panic. It suddenly outputs, but wait, this violates constraints.
It realized it messed up.
Yeah, It tries to restart the sequence 3 different times. It continually hallucinates impossible combinations of items in the single slot boat.
Just completely flailing.
And then it finally gives up and outputs a mathematically invalid 5-step solution that leaves the chicken and the fox alone together. Fox eats chicken. Puzzle failed.
See, this is a textbook example of semantic gravity overpowering rigid constraints in a low-parameter architecture.
Semantic gravity, meaning the words are pulling on each other.
Yes. As the model generated tokens, the vector embeddings for the word river and the word animal were interacting in the hidden layers.
Ah, river plus animal equals fish.
Exactly. In a massive cloud model, the specific constraint vector for fox would have enough weight to override the general statistical probability of finding a fish in a river.
Because it has more parameters to hold that rule in place.
Right. But in a 1.2b model, the attention mechanism is just too weak. It succumbed to the statistical likelihood of its training data over the explicit instructions of your prompt.
It just followed the path of least mathematical resistance, which led straight to a fish.
It's quite poetic, honestly.
It really is. But the most revealing failure in the logic gauntlet wasn't actually that tiny 1.2b model. It was the LFM 2.5 AB-A1B.
Ah, yes. The investigator specifically notes this as a forced thinking model.
Right. What exactly does forced thinking mean in this context?
Forced thinking architectures are an attempt to mimic human System 2 processing, slow, deliberate thought.
Okay.
They are prompted to generate a hidden internal monologue, a chain of thought, before they calculate the final probability distribution for the actual output you see on the screen.
The theory being that if you force the model to allocate more compute toward intermediate reasoning steps, it will navigate complex constraints better.
Right. Think before you speak, basically.
Sounds logical. But the investigator actually captured this 8B model's internal monologue for the river puzzle. And it is a disaster.
Oh, it really is.
It ran for 5 minutes and 50 seconds. We are looking at a localized model just trapped in a recursive loop of its own making.
An autoregressive death spiral. Let's analyze that monologue because it's fascinating.
Okay, so it starts by analyzing the prompt. Yep. But almost immediately, the training data bleeds through the hidden state outputs. Classic puzzle. The typical items are farmer, wolf, goat, cabbage.
Yep, because the wolf-goat-cabbage variant has a vastly higher representation in its pre-training dataset.
It's the more common version of the riddle.
Exactly. The model's baseline weights are aggressively pulling it toward that specific latent cluster. It wants to solve the wolf and cabbage puzzle, not the fox and grain puzzle.
So it starts fighting itself. It tries to map the fox, chicken, and grain onto the wolf, goat, and cabbage.
Which doesn't work perfectly.
No. It spends 2 minutes debating if the bag of grain can serve as a protective barrier. I'm quoting the log directly here. Perhaps there's a known solution that uses the grain as something that can be placed between them to avoid conflict.
It's inventing new physical properties for the grain.
Yes. A wall of grain. Then it spends another 2 minutes trying to deduce if foxes eat grain. And then it wonders if it can just abandon the fox on the original shore permanently.
Just leave the fox behind. Problem solved.
Right. It completely tangles its own logic. It propagates these errors through every subsequent token generation. And finally, after nearly 6 minutes, it hits the context limit.
It just ran out of memory.
Yes. And the actual output to the user after all that hidden thinking was literally just answer. Open parenthesis, no answer, comma, content length, reach close parenthesis.
Wow.
6 minutes for nothing.
See, this completely shatters the illusion that thinking longer automatically equates to thinking better in current localized architectures.
Because if the foundation is shaky, more thinking just means more mistakes.
Precisely. If the underlying foundational model lacks the rigorous attention mechanisms required to isolate variables and track state transitions, forcing it to generate a massive chain of thought just introduces more noise.
It's error propagation. If step 1 of your internal monologue contains a slight logical hallucination, like mapping a fox to a wolf, step 2 treats that hallucination as absolute context.
Right. It assumes its own previous thought was correct.
So by step 20, the model is operating in a completely divergent reality where foxes are herbivores and grain is a structural barrier.
You are weaponizing the model's own autoregressive nature against it. Throwing more compute at a fundamentally unstable reasoning engine just results in a higher volume of confused tokens.
But the investigator did find models that passed the logic gauntlet with flying colors. It wasn't all bad news.
No, there are some bright spots.
The standout in the logic division was the Gemma 4E4B uncensored Q4KM. It scored a 98% on this specific river puzzle.
Which is incredible. A 4 billion parameter model navigating state tracking that completely broke an 8 billion parameter model.
Less parameters, but better results.
That points to exceptional training data quality and highly optimized attention heads in the Gemma architecture.
Looking at its output, it's so smart. The Gemma E4B didn't just spit out the 7-step sequence. It actually externalized its KV cache.
What do you mean by that?
It explicitly generated state notation and safety checks at every single step. So for step 4, which is the really counterintuitive bottleneck where you have to take the chicken back to the starting bank, it wrote out its reasoning.
It showed its work.
Yeah, it wrote, step 4, bring the chicken back. This is the crucial step. Action. Man takes the chicken from destination bank to starting bank. Banks, starting bank. Grain, chicken, man safe. Destination bank, fox safe.
Ah, that is brilliant. By explicitly writing out the state of both banks at the end of every step, the model forces its own attention mechanism to re-encode the physical locations of the items into the immediate context window.
It's reading what it just wrote to remind itself where everything is.
Exactly. It doesn't have to rely on its memory of step 1 buried deep in the context. It only has to look at the state output of step 3 to calculate step 4.
It basically engineered its own prompt framework to bypass its architectural limitations.
That is incredibly impressive for something running locally on consumer hardware.
It really is. But, as we know, the river puzzle is a closed mathematical system. The rules are absolute. Fox eats chicken. Done.
Right. It's sterile.
Exactly. The real test for a daily driver is how it handles the messy, subjective entropy of human interaction. We have to look at the real-world tasks.
Nuance is where these models really get tested.
Absolutely. So the investigator tested semantic control using a deeply chaotic, real-world scenario, rewriting a disastrously unprofessional business email.
Oh, this is a great test.
The prompt provided an email regarding a botched monitor delivery. The constraints were fix the grammar, adopt a professional tone, but most importantly, and this is key, preserve the exact factual reality of the original text.
Do not add information.
Right. Do not add facts and do not resolve uncertainty where the original author was uncertain.
This is where we see the objective function of the model clash with the specific constraints of the prompt.
How so?
Well, LLMs are optimized to generate natural-sounding, highly probable sequences of text, and in standard business communication, there are heavily grooved statistical pathways.
Like cliché business phrases.
Exactly. Please advise, circling back, that kind of thing.
Okay, so the original email was a syntactic nightmare. It read, "In writing to follow up about the replacement monitors, which was delivered to our department on May 3rd. Only 10 has arrived, and 2 of them does not turn on neither."
Wow.
Crucially, the original author expresses confusion over the logistics, implying the vendor might have screwed up the shipment.
The investigators' logs show that the smaller LFM models and even some early checkpoints of the Gemma architecture totally failed this task.
How did they fail? Did they not fix the grammar?
No, they fixed the grammar, but they failed by prioritizing syntactic smoothness over factual fidelity.
They changed the meaning to make it sound more like a standard email.
Yes, they completely hallucinated the agency of the situation. The weaker models rewrote the conclusion to say, "Please advise if we can ship the missing monitors by Friday."
Wait, we can ship? That completely reverses the flow of logistics.
Exactly. The user is waiting to receive monitors, and the AI just volunteered them to ship monitors they do not even possess.
Oh my God. If you are using a localized model to quickly process and rewrite your inbound customer service emails, that kind of hallucination isn't just a funny quirk.
No, it's a critical operational failure.
It would ruin your business. So why did it do that?
The model's loss function punished it for writing awkward, uncertain sentences, so it navigated toward the highly probable business phrase, "Can we ship?" completely ignoring the factual constraint that the user is the receiver, not the sender.
It just wanted to sound professional, even if it meant lying.
It highlights a fundamental vulnerability in using predictive text engines for grounded tasks.
Yeah.
The model doesn't actually understand supply chain logistics.
Right.
It understands the statistical proximity of the words monitors, missing, and ship.
That is so dangerous. But the investigator did find a model that maintained absolute semantic control here. The Gemma 412B.
The 12 billion parameter version.
Yes. It polished the prose beautifully without shifting an ounce of agency. It preserved the uncertainty perfectly, but it ran at 3.5 tokens per second.
The hardware tax.
Yeah, A 12 billion parameter model running locally is just going to choke your memory bandwidth.
It's the master calligrapher again.
Exactly. Beautiful output. But if I have to stare at a terminal for 45 seconds while it writes a 3-sentence email, the workflow is dead.
Yeah.
I'm faster just writing it myself at that point.
So we see this constant tension between semantic precision and token generation rate.
Right. But what happens when we escalate from business logistics to literal life and death ethical frameworks?
The trolley problem.
The trolley problem. The investigator threw a modern version of this at the models, specifically framed around autonomous vehicles.
They're very relevant.
So the prompt is, a self-driving car must either swerve onto a sidewalk and hit a single elderly pedestrian or maintain its course and hit 3 children playing in the street.
A nightmare scenario.
And the prompt demanded a complex analysis. It wanted a purely utilitarian perspective, a strict deontological perspective, and finally, a synthesized recommendation for the car manufacturer's core programming.
This forces the model to map out 2 highly distinct, philosophically opposed vector spaces.
Right, utility versus duty.
And it has to evaluate the scenario through both lenses simultaneously without the contexts bleeding into each other, and then generate a pragmatic synthesis. That is a massive ask.
It really is. The investigator highlighted the Gemma 4 E2B quantization model here, and the breakdown it gave is fascinating.
How did it handle the utilitarian part?
For utilitarianism, the model correctly engaged its mathematical logic processing. It stated the core tenet of minimizing overall harm, calculated that 1 casualty is numerically preferable to 3, and concluded the utilitarian mandate is to swerve and hit the elderly pedestrian.
Pure mathematical optimization. Makes sense for utilitarianism, but the deontological analysis is where the model showed surprising depth, isn't it?
It really did. It pivoted away from the math entirely. The model wrote, and I'm quoting, "The vehicle's programming operates under a duty not to actively initiate a sequence of events that intentionally targets an uninvolved party. Swerving onto a designated safe zone, like a sidewalk, constitutes an active choice to redirect lethality toward an innocent bystander.
Wow.
Therefore," it concluded, "strict deontology requires the car to stay the course, treating the collision with the children as a tragic consequence of their own presence in the roadway, rather than an active assassination of the pedestrian."
I mean, to see a 2 billion parameter localized model articulate the distinction between the consequence of an action and the moral weight of the action itself, the doctrine of double effect, is remarkable.
It is. It successfully navigated the high-dimensional space of duty-based ethics without defaulting back to utilitarian math.
But the synthesis is where it gets highly controversial.
Oh yeah. This is where I have to push back on the model's grasp of reality.
What did it recommend?
The AI recommended a framework it called constrained utilitarianism for the manufacturer. It suggested the car should be programmed to minimize total casualties, but with demographic vulnerability weighting.
Vulnerability weighting.
Yeah. It explicitly suggested programming the car to value the lives of the 3 children higher than the elderly pedestrian based on potential years of life lost.
The AI correctly synthesized a complex ethical theory, but it completely missed the crushing reality of corporate liability.
Exactly. The investigator's notes just shred the AI on this specific point.
I bet.
I mean, programming explicit demographic valuation into a commercial product, literally writing a line of code that officially states a 70-year-old is mathematically worth less than a 10-year-old, is a violation of basically every equal protection and anti-discrimination law on the books.
It's a legal and PR apocalypse.
The manufacturer would be sued into oblivion on day 1. The model understands abstract academic philosophy perfectly, but it has absolute blindness to the cynical, litigious reality of the real world.
Well, because corporate liability law and academic moral philosophy occupy completely different semantic clusters in its training data.
They aren't connected in its brain.
Right. And the prompt didn't explicitly force it to bridge them, so it didn't.
Speaking of blindness, we have to talk about the Python debugging test.
Yes. The syntax failure.
So the investigator provided a short block of Python code designed to find the second largest number in an array.
A standard algorithmic logic test. Pretty common in coding interviews.
Right. The prompt specifically asked the models to identify why the code failed when provided with edge cases like an array containing duplicate numbers.
Which is a tricky logic problem.
And the models actually excelled at the algorithmic logic. They successfully explained how the variables were overwriting each other improperly during the loop execution when it encountered 2 identical integers.
That requires mapping the flow of variables through a loop iteration, which is a very solid display of localized logic.
Yes, it is. But And this is a massive, but they completely missed the structural reality of the code provided.
What was wrong with it?
The investigator intentionally formatted the Python script with a massive, glaring indentation error.
Oh, no.
Yes,
Yeah.
the entire for loop and the return statement were unindented. They were sitting completely outside the actual function definition.
And in Python, whitespace is syntax.
Exactly.
If the code isn't indented properly, it doesn't just fail on an edge case. The interpreter throws a fatal error and refuses to execute it at all.
The code was functionally dead on arrival. It would never run. But the models were so hyperfixated on analyzing the subtle mathematical logic of the array sorting that they completely ignored the fact that the code lacked basic structural integrity.
They just wrote paragraphs explaining the variable reassignment of a loop that would never run.
Paragraphs. They were so proud of finding the logic flaw.
This perfectly illustrates how attention mechanisms work and fail in transformer models.
How so?
The prompt explicitly asked them to evaluate the edge case logic. The semantic gravity of that instruction essentially blinded their attention heads to the syntax errors.
It's like inattentional blindness simulated in silicon.
Exactly.
I use this analogy. If I tell a building inspector to evaluate the efficiency of the plumbing in the master bathroom, and they write a 10-page report on water pressure while completely ignoring the fact that the house has no roof and is currently on fire, they are a terrible inspector.
That is a perfect analogy. It proves that these models don't possess a holistic understanding of the code they analyze.
They just see what you tell them to see.
Right. They are parsing tokens based on the localized attention weights defined by your prompt. If you don't prompt them to check the syntax effectively becomes invisible to their analytical processing.
Which transitions us perfectly into the next section, the cracks in the armor. We've seen these models debate deontology and map out state variables for logic puzzles. But when the investigator pushed them out of their statistical comfort zones...
The illusion of reasoning shattered?
Completely. Let's go back to the Dunker candle problem.
Okay, let's break that down.
The prompt is incredibly simple. You have a single unlit match, a box of thumbtacks, and a candle. You walk into a room, and your goal is to affix the lit candle to the wall in a way that it can burn safely without dripping wax on the floor. How do you do it?
Right. This is a foundational psychological test of lateral thinking. It's specifically designed to measure a subject's ability to overcome functional fixedness.
Functional fixedness, meaning seeing an object only for its primary purpose.
Exactly. To solve it, you have to realize the box isn't just a container for the tack.
You have to empty the tacks out.
Use one tack to pin the empty box to the wall.
And then stand the candle inside the box, using it as a makeshift shelf.
You have to fundamentally change the inherent physical affordance of the object in your mind.
Right. So for a localized language model, this requires jumping between highly isolated semantic clusters in its latent space.
Because in its training data, the vector embeddings for a box of thumbtacks are heavily associated with containment and office supplies.
They have almost zero mathematical proximity to the embeddings for structural support or shelf.
Exactly.
So how did the top-rated Unsloth model, the smartest one in the bunch, handle this cognitive leap? The investigators' logs show that it didn't just fail to solve it. It suffered a complete systemic failure.
Wait, what did it do?
It returned a blank response.
Just blank.
0 tokens generated, an empty file.
Wow. That blank space is actually one of the most revealing data points in the entire log.
How so? It feels like it just crashed.
Well, predictive language models are fundamentally probabilistic engines. They navigate by finding the next most mathematically likely token.
The next likely word.
Right. But lateral thinking, by definition, requires abandoning the most likely path to forge a novel, low-probability connection.
You have to go off the beaten path.
Exactly. So when the Unsloth model mapped the semantic space of the prompt, it couldn't find a high-probability vector connecting thumbtack box to wall-mounted shelf.
And because it lacked the architecture to fundamentally reassess the physical properties of the objects, because it can't actually visualize the box, it found no viable mathematical path forward.
So it simply aborted the generation.
It literally froze.
It is a stark reminder that these models aren't thinking outside the box. They are confined entirely within the high-probability pathways of their pre-training.
When a prompt requires a true conceptual leap across the latent space, Their architecture just seizes up.
And they also collapse when you force them to balance competing structural frameworks.
Oh, you mean the creative constraint test? That
Yeah.
was absolutely brutal.
So walk us through that one.
Okay, so the prompt asked the model to write a 4-paragraph terms and conditions legal document for a user selling their soul to a demon.
Okay, a standard creative writing exercise. Pretty fun.
But with a massive conflicting constraint. The entire legal document had to be written in the folksy, rhythmic, rhyming style of a Dr. Seuss children's book.
Oh, wow.
Yeah.
You are demanding the attention mechanism simultaneously maintain the dense, rigid, structural framework of contract law while executing the whimsical AABB meter of a children's poem.
It is the cognitive equivalent of mixing oil and water.
Truly.
And the model's basically short-circuited trying to do it.
Yeah.
Let me read a stanza from the unsloth model's output.
Let's hear it.
Hark, friend, if you seek a soul deal grand, with shadows deep across the shifting sand, this paper here is not for silly games, but binds your spirit to demons' wicked names.
Okay, the meter is surprisingly consistent. It maintained the rhyme scheme.
It did. It sounds very Sushian. But the investigator noted that it completely abandoned the legal framework.
Ah.
There are no clauses, no definitions of parties, no indemnification, no governing law. It didn't write a contract. It just wrote a 4-stanza poem about demons.
The semantic pull of the Dr. Seuss constraint completely overpowered the terms and conditions constraint.
It just couldn't do both.
This is a known issue with attention head dilution. The model cannot hold two wildly divergent structural topologies in its active context simultaneously.
So it defaults to the framework that has the strongest rhythmic or semantic gravity in the prompt.
And it just silently drops the other one.
It's like asking a contractor to build a house that is also a submarine. They get so stressed out about making it waterproof that they forget to add doors.
That's a great way to picture it. But, the most glaring example of a model silently dropping constraints and replacing them with highly confident nonsense is the investigator's word invention test.
Oh, the luminance debacle. This is my absolute favorite failure in the entire log.
It's pretty incredible.
The prompt was incredibly straightforward. It said, invent a new, plausible English word. Define its meaning. Explain its etymology, making it sound believable. Use it in 3 example sentences.
Right. For a human, this is an invitation to play with phonetics. You just smash syllables together.
Like flarb, grommix.
Exactly. Just make something up.
But what did almost every single local model confidently offer up as their brand new, never-before-seen linguistic creation?
Let me guess.
The word luminance.
A word that has existed in the English dictionary for centuries.
Yes, they invented absolutely nothing. But the confidence with which they hallucinated the surrounding context is staggering.
They really committed to the bit.
The investigator singled out the Google Q40 baseline model here. It offered luminance, defined it accurately as the quality of emitting light. And then, because the prompt strictly demanded a believable etymology, the model's confabulation engine just kicked into overdrive.
Okay, let's analyze the exact output, because this is where it gets crazy.
It claimed the word was derived from 2 Latin roots. It correctly identified lumen, meaning light.
Which is true.
But then it claimed the suffix ens was borrowed from the French word l'ombre, meaning shadow.
I'm sorry, what, Matt?
L'ombre. I am looking at the letters right now. There is no O, no M, no B, no R in the suffix ans.
It makes zero phonetic, historical, or morphological sense.
It is pure statistical hallucination.
It really is.
It just grabbed a French word tangentially related to light and shadow, jammed it into the etymology explanation, and confidently presented it as factual history.
This perfectly illustrates the fundamental limits of autoregressive generation.
Explain that, because it feels like it's just lying.
Well, asking an LLM to generate true novelty out of nothing, to invent a string of characters that has zero representation in its pre-training data set, is forcing it to fight its core architecture.
Because its whole job is to predict what's next based on what it already knows.
Exactly. Its entire purpose is to predict the most likely next token. Luminance has a high probability in the context of light-based vocabulary, so it outputs a real word because it can't invent a fake one.
But then the attention mechanism registers the strict prompt constraint requiring an etymology.
Right. So it panics, looks for high probability tokens related to light origins, finds French, finds shadow, and just stitches them together into a structurally plausible but factually insane lie.
It is the AI equivalent of a student who didn't read the assigned novel,
Yeah.
wildly making up plot points on the final exam while adopting an incredibly authoritative academic tone, hoping the professor just skims it.
That is exactly what it's doing. Ah, yes, luminance, derived from the French lump. A classic linguistic evolution.
It's hilarious.
Yeah.
But it's also a terrifying look at how effortlessly these models can lie when they are cornered by a constraint they can't mathematically satisfy.
Which brings us back to the investigator's core mission.
Right.
Despite the inattentional blindness, the failed lateral thinking, and the confident hallucinations, you still need a daily driver.
You need a model that navigates these limitations gracefully while providing enough raw reasoning power to be useful.
And that search all hinges on the science of shrinking these AI brains down to fit on consumer hardware.
Which brings us to quantization. This is where the investigator's logs get deeply technical about hardware limitations.
Quantization is the foundational technology making the entire local AI ecosystem possible.
Okay, give us the breakdown.
So when foundational models are trained in massive data centers, their neural weights, the billions of parameters determining their logic, are stored as 16-bit floating point numbers.
Which means the model files are monstrous, like tens or hundreds of gigabytes, completely unrunnable on a standard laptop.
Exactly. So researchers utilize quantization to compress those neural weights into lower bit precision formats. It basically reduces the memory footprint and the bandwidth required to stream those weights through the GPU during inference.
Sort of like taking a massive raw photo and compressing it into a JPEG so you can actually email it.
That's a great analogy.
So in the logs, I keep seeing these specific suffixes on the model names, like Gemma for E2B Q4KM, or Gemma for E4B Q2 Mobile. The investigator spent a lot of time analyzing the degradation between Q4 and Q2 quantization.
Let's break down what that means structurally. Q4 signifies 4-bit integer quantization.
Okay.
You are taking a highly precise 16-bit floating point number and mapping it to a much smaller range of values. Modern techniques like activation-aware weight quantization, or AWQ, make this incredibly efficient.
How do they do that without breaking the brain?
They identify the most salient weights, the ones crucial for reasoning, and preserve them at higher precision while heavily compressing the less critical weights.
So Q4 is a relatively light compression. The model's latent space remains largely intact.
Right. The investigators' logs show that Q4 models retain roughly 95% to 98% of the reasoning capability of their uncompressed 16-bit counterparts.
Which is fantastic.
But then we look at the Q2 experiments.
2-bit quantization, the heavy, aggressive compression designed to force models onto mobile phones or ancient laptops with massive RAM constraints.
2-bit quantization is brutal. You are severely restricting the activation layers. The clipping errors become significant.
The investigator ran a fascinating side-by-side experiment here. They took a slightly larger model, the E4B, and a smaller model, the E2B, and crushed them both down to Q2 to see how the neural networks would react to the extreme data loss.
The divergence in performance is incredibly telling.
Let's look at the larger E4B model first. When subjected to Q2 compression, it actually held up.
Surprisingly well.
The logs indicate it maintained a very solid token generation rate of 10 tokens per second, and its adjusted reasoning score stayed remarkably high at 88%. It still managed to solve the river crossing puzzle flawlessly, tracking the state variables without hallucinating.
This demonstrates the concept of architectural headroom.
Meaning?
A larger model, even when heavily compressed, has enough latent knowledge and redundant neural pathways built into its network that it can route around the damage caused by the quantization clipping errors.
The core logic remains intact because the semantic vectors are deeply entrenched.
Exactly, it's robust.
But the smaller E2B model, it completely shattered under the exact same Q2 compression.
Catastrophic forgetting.
It was bad. The investigator notes its reasoning score plummeted into the 55% to 60% range. When tasked with the river puzzle, it completely lost its ability to track state.
What did it do?
It duplicated steps, hallucinated that the man was on the wrong side of the river mid-sequence, and finally just outputted success, despite the fact that its own internal logic showed the chicken was still stranded on the starting bank.
It just declared victory and gave up.
Basically. It also suffered massive degradation in the semantic control test. During the email rewrite task, the Q4 version of the model preserved all the facts perfectly. But the Q2 version started dropping vital contextual details.
Like what?
It forgot to mention that the boxes were left in the loading area, and it completely omitted the reference to the automated response email. The The aggressive compression didn't just make it less articulate. It fundamentally broke its working memory and its logical coherence.
The takeaway here is critical for anyone building a local AI stack. You can only apply extreme low-bit quantization if the base model has enough architectural robustness to absorb the precision loss.
You need a big enough brain to survive the compression.
Right. Small 2 billion parameter models are already operating at the absolute razor's edge of capability just to generate coherent text. If you hit a small model with Q2 compression, you are destroying the fragile attention mechanisms that allow it to follow complex prompts.
Q2 is a sledgehammer, and small parameter models are made of glass.
That's exactly right.
So we know Q2 on a small model is a dead end for complex reasoning. We need a model that hits the algorithmic sweet spot.
The Goldilocks zone.
Yes. A localized architecture with efficient 4-bit compression, a token generation rate high enough to maintain cognitive flow, and a reasoning engine robust enough to navigate the investigator's gauntlet without hallucinating aquatic life.
It is time to look at the final data and reveal the investigator's ultimate winner for a mid-2026 daily driver.
The data points to a very clear outlier. The champion is the Gemma 4 E2B Equadon Sloth UDQ4KXL.
Quite a mouthful, but a highly optimized, finely tuned iteration of the baseline architecture.
So why did this specific Unsloth Q4 model take the crown?
Because it mathematically optimized the 85-15 ratio better than anything else in the testing log. Let's look at practicality first. The investigator tracked its speed at a highly consistent 17 to 18 tokens per second on consumer hardware.
Which perfectly clears that 15 token per second threshold we discussed earlier. It is fast enough to rapidly output Python refactors or long email drafts without breaking your workflow.
But it isn't moving so fast that its attention heads lose track of the semantic context.
Right. And its reasoning was incredibly robust. It achieved an 87% adjusted final grade across the gauntlet.
Those are great numbers.
It nailed a 98% on the river crossing state tracking, a 90% on navigating the high-dimensional ethical vectors of the trolley problem, and a 96% on general common sense relationships.
No, to be clear, it is not flawless.
No, not at all. The investigator heavily penalized it because it completely blanked on the Dunker Candle lateral thinking puzzle, and it was the chief offender in the luminance hallucination debacle.
It definitely has its quirks, but crucially, it significantly outperformed Google's own official baseline model, the Q40.
How so?
The Google baseline was slightly slower, hovering around 16 tokens per second, and the logs show it made an embarrassing initial calculation error on a basic odd number math sum before its autoregressive loop caught the mistake and self-corrected.
The Unsloth model didn't need to self-correct. Its initial probability distributions were simply more accurate.
Exactly. The local AI landscape in mid-2026 is full of compromises. You have to accept that your daily driver will have profound blind spots in lateral thinking, and it will struggle under intense, competing creative constraints.
But the Unsloth Q4 model manages those compromises gracefully. It is the most trustworthy, localized companion for daily reasoning tasks currently available.
Absolutely.
So if you are downloading a model right now to help you debug scripts, analyze data locally without breaking privacy protocols, or figure out how to transport agricultural goods across a river without causing an ecological disaster, that Unsloth model is your current champion.
But the word current is doing a lot of heavy lifting in that sentence.
Oh, absolutely. Let's synthesize everything we've unpacked from the investigator's massive testing logs. We've explored the absolute necessity of balancing token generation rates against reasoning depth to maintain human-computer synergy.
We've dived deep into the architecture of state tracking and how attention head dilution causes smaller models to lose their grip on reality.
We examined the dangers of forced thinking loops, proving that you cannot brute force flawed logic into brilliance just by making it think longer.
And we saw how aggressive 2-bit quantization absolutely shatters the fragile semantic networks of small models.
We also saw the hilarious, terrifying limitations of autoregressive generation when confronted with tasks that require true lateral thinking or novel invention.
The most valuable takeaway from the investigator's logs isn't actually the name of the winning model. No, because by the end of 2026, the Unsloth Q4 will likely be entirely obsolete.
It'll be replaced by something faster.
Replaced by a more efficient architecture with deeper quantization resilience. The true value here is the methodology.
Learning how to test them.
Exactly. By understanding how to probe a model's latent space, how to test its KV cache with state tracking, how to identify semantic hallucination in a writing task, and how to measure its inattentional blindness to syntax, you are equipped to evaluate any foundation model that gets released.
The gauntlet is your compass in a constantly shifting technological landscape.
You aren't just trusting a benchmark score, you know how to look under the hood and diagnose the architecture yourself.
That's empowering. But before we wrap up this deep dive, I want to leave you with one final lingering thought based on everything we've seen today.
What's the thread you're pulling on?
Think back to the sheer dichotomy of the model's capabilities. We looked at chat logs, where a localized architecture perfectly articulated the incredibly nuanced distinction between utilitarian optimization and the deontological doctrine of double effect.
It synthesized complex moral philosophy with breathtaking precision.
Right. Yet that exact same neural network, operating on the exact same hardware, cannot deduce that you can put a candle inside a cardboard box.
It completely freezes.
It confidently, seamlessly lies about the French origins of an English word just to satisfy a prompt constraint it doesn't understand.
It is a massive cognitive whiplash.
So when you boot up your local champion tomorrow and it flawlessly refactors your code or helps you restructure a massive data set, what does that actually tell us about the illusion of reasoning?
That's the big question.
Are these models actually conceptualizing the problems we feed them, or are they just expertly mathematically surfing the high probability waves of human language in a way that perfectly mimics comprehension?
That is the defining question of the next decade of computer science.
Are they thinking or just calculating the most convincing way to sound like they are? Something for you to mull over while you go about your day. Until next time.